Hello, Geometry Advanced students. So here's some extra examples for the notes from lesson 10.4, which is on secants and tangents. So if we start with this first problem, it says circles tangent at T. So again, notice I have two circles here. They're tangent at T. That means they meet at T. Have centers at M and N. Line ST in the middle here is tangent to both circles at point T. We want to find the radius of the smaller circle. And in the picture, that would be circle M. If SN and segment SN, so segment SN and segment SM are perpendicular. So again, that means I have a right angle here at S. And again, since line ST is tangent, remember we had a theorem that said the radius and the tangent line are perpendicular at the point of tangency. So I have right angles at both of those positions. So what I would recommend doing first is looking at the big triangle itself. If I highlight it here in yellow, we know that angles of a triangle have a sum of 180. I know it's kind of faint here, but angle N is 35 degrees. So if angle N is 35 and this angle here, MSN, is 90, I can find angle M. So if I add the angles together and subtract from 180, angle M is going to be 55. Okay, so now that I have that, what I probably want to focus on then is this triangle here. It's turquoise or bluish. Since I want to find the radius of the circle, that would be like segment MT. So if I call that X, so with respect to the 55-degree angle, X would be the adjacent side and 8 would be the hypotenuse. So if I'm using trig ratios and I'm thinking about adjacent and hypotenuse, I should be using cosine. So we're going to have the cosine of my angle, which is 55. That equals the adjacent, which is x, over the hypotenuse, which is 8. So I'm going to grab my calculator, and I'm going to turn it on, obviously. And I'm going to type in the cosine of 55. And 4 places after the decimal is going to be 0.5736. So 0.5736, and again that equals x over 8. So to solve for x, we could multiply both sides by 8. And if I specify in the problem, since it didn't say in the directions, let's round our answer to the nearest tenth. So if I take that times 0.8, I get about 4.6. So that's going to be, x is referring to the radius of circle M. So that's going to be the radius. Okay. So again, a lot of these problems in these circle lessons, even though we're talking about circles, come back to right triangles. This one used trig, and some of the other ones we used special right triangles or Pythagorean theorem or your Pythagorean triples. They keep coming back, so keep that in mind. Okay, in my other example, it says two circles that are externally tangent have radii of 12 inches and 8 inches respectively. Find the length of the segment, tangent segment AB. So the one I want to find in the end is this length here. So what I'm going to do first is I'm going to draw a segment that connects D through F and then out through A. So again, if we know the radii of the circles are 12 and 8, the bigger one would have the radius of 12. The smaller one would have the radius of 8. And this length from F to D would be 12 plus 8, which is 20. So what I want to do first is I want to figure out this length of BC. We'll call that x. So remember again, the radius and the tangent are perpendicular at the point of tangency. So I have right angles at C and B. We did a problem like this before. What this figure is a trapezoid. So if I pull it out of the picture and rotate it, it looks like this. So again, this is B, this is C, here is D, and that's F. So if we know DB is 8 and FC down here is 12, and we also know DF is 20. So what we're going to want to do is we're going to drop in a height. So if we want to find BC, we'll call it X. We're going to drop in a height here. We'll call it X. So I made a rectangle and a right triangle. So if DB is 8, the segment at the bottom here is 8, and then 12 minus 8 is 4 for this end. So again, now, if we focus on this right triangle here, we could use Pythagorean theorem to find x. We cannot use triples because 4 and 20 aren't part of one of our triples, and if I divide them by 4, 1 and 5 are not part of our triples either. So again, we have to resort back to Pythagorean theorem. So we're going to do x squared plus 4 squared equals 20 squared. 4 squared is 16, 20 squared is 400. So if I continue solving for x, if I subtract 16 from both sides, that's going to give me 384. And now I'm going to simplify. So I'm going to take the square root of both sides. So 384 is not a perfect square, but if I'm not mistaken, it's divisible by 64. So we're going to say it's the square root of 64 times the square root of 6. So that's going to be 8 root 6. Now, again, that's not my final answer. That is just the segment right here, BC. Again, it's 8 root 6. But remember, keeping in mind, I want to find AB. That's my final answer. So to continue with this, what I would recommend you doing next is focusing on similar triangles. So let me grab some colored pencils here. Okay, so what triangles I'm talking about, if you can see me tracing here, I'm looking at this pink one here and the big one. So again, those two triangles are similar. And if you remember when we covered similar triangles, remember their sides are proportional. So if I write a proportion, I could do something like 8 over 12. And that equals x over this whole side would be x plus 8 root 6. So what we're going to do is solve our proportion. But what I would recommend doing first is simplifying. So for example, 8 over 12 are reduced to 2/3. And then now if I do cross products, I'm going to have 3x equals 2 times the quantity 2 times the quantity x plus 8 root 6. If I distribute, so again I still have 3x on the left, we're going to have 2x plus 16 root 6. And then if I finish solving, I would subtract 2x from each side. 3x minus 2x is x. So x is going to be 16 root 6. Now I probably should not have used x. My mistake. I probably should have used y because these two x's are not the same. So let's just change that to a y so we don't get confused. So my AB length is going to be 16 root 6.